I would like to talk about a place where tensor categories also appear, which is in the context of non-topological defects. So this talk will have a fairly long physics motivation, where we will meet a sort of mildly non-topological defects. I'll tell you what these are. Then I point at a question which arises from the physics motivation, which I want to model algebraically. And so that will be part 2. I'll give the algebraic description of that question. It'll be a fairly standard thing. It'll be Jetter-Drinfeld modules or a version of Jetter-Drinfeld modules. So there's sort of no new mathematics here, if you want. So maybe the thing which could be interesting here is that there is a relation between this question and that algebraic structure. And if you and so this physics motivation poses some specific questions on some specific algebraic problems of which I don't know the solution or even how to say them precisely. So that may be interesting to look at. So that is maybe the takeaway, hopefully at the end of the talk. And I'll also do one example which is related to UQSL2 heads, so affine quantum SL2. Right. So we go into the physics motivation. So one place where higher categories appear, if you want, is in d-dimensional quantum field series. And the expectation is that if you look at the topological defects of various dimensions in the d-dimensional quantum field theory, then that should somehow define for you a d category of topological defects. So a d-dimensional quantum field theory should hand you, or the collection of all of them should hand you a d category of topological defects. In dimension 2, you can make that fairly precise. So there you would get two-dimensional quantum field theories, and they should hand you a 2 category of topological defects. And the ones I want to look at, they satisfy certain finiteness conditions reflected in that my 2 category here will have adjoints. Specifically, if you take one quantum field theory, you can look at all of its sort of the endomorphisms in these 2 categories. So this would be topological defects which just live inside a given quantum field theory. And so these would form some pivotal monoidal category. Okay. So higher categories arise in quantum field theory. What's an application of that observation? So if you have never seen that before, that may look a bit arbitrary, but one application is the study of something called renormalization group flows. So what is that? So in that setting, you have 2 conformal field theories. One is often referred to as ultraviolet conformal field theory, and one is often referred to as infrared conformal field theory. And they are related by a family of non-conformal or possibly non-conformal field theories, so just 2-dimensional quantum field theories. And you should think of this as a flow where you have a theory which at short distances looks like this, and at very large distances looks like this, and this describes all the intermediate scales, if you want. But it's a family of quantum field theories at whose end you can somehow put a conformal field theory. Then, again, as we actually briefly heard in the first talk of this conference by Christoph, one way in which in physics you would parameterize such deformations, if you want, is by pointing at a field in the ultraviolet theory. So this somehow a way of talking about the tangent space of these fields, and then you can deform a theory in that direction. So that's what this symbol here means. And a very difficult question is if you start with a theory you understand well and you deform it, what is the end of that deformation, if that even exists? So if I hand you this theory and the deformation, so I hand you the ultraviolet theory and I point at the direction in the tangent space, then where does this flow go? Right, and so one application or one place where these topological defects or the higher categories which come with them are useful is to try and put constraints on what this endpoint theory can be. So that's my little cartoon here. So you have your starting theory, which is some conformal field theory. It'll have some collection of topological defects. Then there'll be a small subset which is preserved, or there may be, that may be trivial, but suppose there is a small subset which is preserved along the entire flow. Well, then that subset should also be present at the endpoint of that flow. There'll be some infrared theory, which again will have some maybe large collection of topological defects, but these have to sit in here. right? So then from that you learn that if you've identified a part of your topological defect, so in tensor category language, some subcategory which is preserved by the flow, then that subcategory has to appear inside the tensor category of topological defects of the endpoint theory.
So this flow depends on the direction that you...
Yes. So, and the direction is sort of dictated by this field. So if you point it at different of these fields, and then the endpoint may change or not change, and both can happen.
Can you flow backwards? That's a key question.
Is it?
In philosophy.
Well, so in a way, so to walk out of this theory and to generate the flow, you have to point in more detail at something called a relevant perturbation. So that's a field of a scaling dimension, which is well, it depends on the dimension of your space-time, but in 2 dimension has to be less than 2. So I guess in D dimension has to be less than D. And then it'll approach this theory in some way. But the observation is that there are only finitely many maybe relevant directions, but there are also always infinitely many irrelevant directions. So this here you can typically deform much more, but then yeah, so then you have to, I will not explain it. So there's a way to do this, but it has an infinite amount of freedom, and you have to choose infinitely many things, and that's the not good direction. Okay, so here's a little morphology of defects. So I talked about topological defects and that they are useful, but there are many more defects in the quantum field theory. So quite generally, you can look at all defects of all dimensions, which are just not topological, which you can't deform without affecting the amplitudes of your theory. Then if you're talking about a conformal theory, well, then there's a special class of defects which are also well behaved under conformal transformations, rather than just under isometries. And in here sit our friends, a special class of topological defects, which is all we've looked at so far. But in this talk, I would like to look at a slightly different class of defects, which are something I want to call translation invariant defects. So they sort of sit slightly, so they're not conformal, but they are defects, and however, they intersect with the conformal defects precisely in the topological defects. So there's a sort of, you can think of these as a slightly different generalization of topological defects other than conformal defects. Okay, so these are the ones I want to, I'll explain what these are, but these are the ones I want.
What's the difference between observables, localized, and submanifolds and defects of some dimension?
Ah, yeah, put that on there. Somebody can be annoyed about it. So
just asking.
I'm saying that not everything you want to call an observable is a defect. So for example, if you just integrate a one form or some form over a manifold, well, that's not a defect because it's not compatible with factorization of, so if, right? So on the other hand, if you exponentiate that integral, well, then that becomes compatible with factorization. So not every observable is compatible with cutting your manifold to pieces. And that's what I would say is the distinction here. Okay, so translation invariant defects. So we look at our 2-dimensional quantum field theory on a cylinder. Here's my cylinder. So that I wanted to, never mind. So these 2 lines are identified, and my defect wraps around the cylinder. And I'm saying I call it translation invariant if I can rigidly shift this defect up and down. So outside here, there may be other stuff which I don't move, but the defect I can rigidly shift without changing the amplitude. So that's, and in general, this will not allow to be deformed in arbitrary ways as one would be used to from topological defects. So this, in general, will be different from this, but you can shift it rigidly. So that's my weaker condition on these defects. So that's my my mildly non-topological defect in the sense that I can shift it rigidly, but not deform it arbitrarily. And and what that means is that the operator on the state space for the defect commutes with the Hamiltonian of the system, right? So it commutes with the generator of translations. Okay, so these are the defects I want to talk about. Why is it nice to talk about them? That's because they also, so this bigger class of defects still hands you back a monoidal category. right? So if you think of where did the structure of the monoidal category and defects in a two-dimensional theory come from, so there's a tensor product which comes from this fusion operation. So you take one defect and another defect, and you move one on top of the other. That process defines the tensor product, and the topological point insertions you have on these defects, they give you the morphisms, right? And I'm claiming that if I have not a topological defect, but a translation invariant defect, I can do the same thing, because of translation invariance, this process here is not singular. Right, so that's what stops you. And if you do this for generic defects, then if you push this here, that'll have quite a bad singularity, and you can't, or so there's no developed theory to say what does that mean to take that fusion? What's the algebraic structure you get out of this? But in this now simplified situation where we look at these translation invariant defects, well, that operation is well defined, and so on the collection of all my translation invariant defects, I do have a tensor product operation, and so they also give a monoidal category. Right, so that's sort of one of the takeaway messages, that there's a monoidal category also for this larger class of defects, which fully contains the topological defects, which we would have normally looked at. So there's a larger, potentially larger monoidal category assigned, which a quantum field theory hands back to you, which contains the one we would have usually looked at, which is the ones of topological. Right. So so now the question arises: so we have examples of this, like if you do the Ising model in two dimensions, then you have the Ising fusion or the Ising modular fusion category here. And so can we say anything about the monoidal categories we get out of this? So that's the question I want to look at a bit. But let's go back to, so maybe that was one reason why these could be interesting. I want to also go back to this application we had with the renormalization group flows to state another reason why this larger class of defects may be interesting. That's maybe more a physics reason, but still good. So that's the situation we had. We had this family of quantum field theories which has a CFT sitting for short distances and long distances, and there may be some topological defects which are preserved along the whole flow, which exist in the same way for this whole family, and so they have to be present both in the UV and the infrared, and we wanted to use this to constrain endpoints of flows. Now, let's make that picture larger. So now I've enlarged the class of defects I look at to this larger set of translation invariant ones, and it could now happen that in addition to having some topological defects which are preserved, maybe there are also some translation invariant ones which are preserved along the flow. And the neat thing is that at the endpoint of the flow, these will also turn topological. So if you can make sense of this process, it'll potentially give you access to a larger class of sort of the topological symmetry of the endpoint of that flow. So I can't actually make that work yet, but that's another motivation to look at the structure. Right, so the statement here is that if you take any defect and you flow it to the endpoint, it'll be some conformal defect over here, and the defect which is both conformal and translation invariant is topological, which is where you have to end up here. Okay, so that's the physics motivation. I want to be able to model this set. I want to have some algebraic model which describes the translation and translation invariant defects which can exist, which are compatible with a perturbation, which can exist along the perturbation. So that's what I want to do. In order to explain the algebraic thing which comes out of this, I need a little bit of more background on how I want to describe CFTs, 2 or 3 slides, and then we go to algebra. Yes?
Can you have topological defects which are preserved in the translation and didn't start with the invariant defects?
Say it again.
You said that when you add the invariant defects and then you do the translation, you add the topological defects.
So I'm
Preserved. Does that cover all the topological defects that are preserved through the process, or could there be more?
so So I would say so that so these are all so I colored it in two different ways, but the topological ones are special cases of translation invariant ones.
It's not, my question is different. There, at the end, at the IRCFT, yeah, could there be topological defects that survive the translation, that the translation weren't invariant, that survive sorry, I'm not.
Normalization flow.
The flow, sorry, thank you. Could there be topological defects that survive the flow and weren't invariant defects to begin with?
So I would say that those which exist along the flow,
Uh,
these will be detected by.
translation invariant, yeah.
So what can't happen is that you end. So this process will not give you something here because at the end point you will automatically.
I understand. My question is different. Could there be topological defect that survive the flow, but they weren't the blue ones to begin with? Or the
If the topological
I would say
translation invariant.
I would say no, but we can talk about this.
okay,
Because
understand.
In this picture, is there a difference between the right endpoint and the left endpoint?
Automatically translation.
that's the start point
saying-
and that's the end point.
Well, like I can't, oh, I see, I can't go back. There's.
So I think the short answer is no, you can't go back. Long and complicated answer, but
Yes, I understand that.
Why doesn't the argument about translation invariant conformal implies topological multiply the left end?
what?
You said there, if a defect is translation invariant conformal, it's topological.
So that means this box goes here.
But at the left end, those are conformal.
No, it's not conformal. These are not
So you're
conformal.
assuming that's a conformal defect.
Are not conformal. These are not conformal. The theory is conformal, but I'm allowed to look at non-conformal defects in my conformal. Yeah.
And then why in the end point does it become conformal before topological?
Well, okay, with Explar, if you reach an RG endpoint, everything conforms. And if it's an RG invariant, so also these, right? If I would flow these, they would go to a topological defect in here. So RG endpoints are expected to be conform invariant often. Okay. So I wanted to give a little bit of background where the algebraic structure I pointed comes from. So we have a two-dimensional conformal field theory, maybe with some topological line and some fields, and I want to model it as a boundary theory to a three-dimensional topological field theory. The ones I will use as a separate holomorphic and anti-holomorphic, but there's two non-conformal non-topological boundary conditions. Which will model the dependence on the conformal structure, and then it has a surface defect which separates the two sides, which will describe different conformal field theories you can build with these non-topological boundary conditions. And field insertions are given by having line defects, which are again in the inside are topological, which stretch, meet my surface defect, and then come out on the other side, and different such fields then described by different point junctions which can sit here. These topological defects are modeled by topological lines which live on the topological surface. So, okay, so the structure, the algebraic structure I want to take out of this is that I want to look at the categories of line defects. The line defects in these three-dimensional regions are, well, you would usually maybe say are described by modular fusion categories. I can maybe be a little bit more general and say they are described by some braided tensor category. For example, if I don't take all lines, but just some of them. And so I have a braided tensor category of lines here, potentially different braided category of lines down here, which in my examples will always be the same, but a priori could be different. And then there's a tensor category of line defects which live on that surface. And so I've got three categories of line defects, braided, tensor, and braided. And I've got two functors which map the line, which amount to taking lines from the 3D regions into the 2D regions. And these are modeled by functors from these braided categories into the Drinfeld center of the lines on the on the surface. And so that looks like a one morphism in Britain's, but that confuses me at the moment because the dimension counting is off, but somebody can maybe help me after the.
The colors of the letters, do they correspond to the colors in the picture?
Not consistently. So this is red, and that line is red. The dot is also red. That's wrong. So, but the lines are described by this, and sort of the dotty green region should be all of this, and that's described by the. Yeah, I think the short answer is no. Okay, so two braided categories. So that's like something which looks like a one morphism in Britain's. So that's what we get out of this. And then I need a condition which I call the bulk commutation condition, which will ensure. So if that is satisfied, that models a defect in the deformed theory, which is still translation invariant in the deformed theory. And I don't want to explain why that works, but I want to state. I want you to maybe briefly look at this condition. So remember that this line here modeled a certain field in my 2D theory, and this red D is a topological defect. The purple thing is the surface defect, and it says that passing my topological defect on one or the other side, so it's a bit like commuting the bulk field past the defect, should be equal to having two junctions which of X with the defect and Y with the defect, and commuting these two junctions. So I'm saying whenever I find a solution to that condition, I can write a translation invariant defect in the perturbed theory. So this is the condition I have to solve. So let's try and write that down in terms of the algebraic data we had. So I want to fix an X in my category C, which were the lines up here, and a Y in my category D, which were the lines down here. Then I have these two functors anyway. And I want to fix such a junction point, which turns out to be a morphism omega in T. So I'm not writing the forgetful functors here, so I'm forgetting down to T, from transporting X to T, tensor transporting Y to T to the unit. So that's if you want, that's the data which describes a specific direction of perturbation. That's a bulk field, but algebraically, I want to look at that data.
Would have asked before, but you assume that UV and IR are both rational.
Well, I would count this as still the physics motivation. So I'm not. My example later will not be rational, so I shouldn't say rational at this point.
And C and D, how do they relate to them? So the C is just representations of UV and D.
I would say you're allowed. Right, so that's why I tried to be. So C doesn't necessarily have to be all line defects. It's the sort of the line defects you're interested in.
So it's
It could be a subcategory of all of them, yeah.
And D is subcategory.
Yeah. Right, so I don't necessarily want to say what are all line defects I can write down in that theory, but just it's still going to be a braided category.
I still want them to close. Yeah. Okay.
Yeah. Right, and okay. So this I keep fixed, and then I want to find all solutions consisting of a choice of line defect D, junctions F and G. So F, how's F disjunction modeled algebraically? You take the object X, you forget it, so you move it up here, then you forget it into T, and then F is just a morphism in T. Similarly, G is just a morphism in T, and I want this data to satisfy this condition. And so that's condition.
A question, a small question. Do you assume when you fix X, Y, and omega, you assume that omega is non-zero? That X and Y are such that omega could be non-zero?
No, omega is a parameter, could be zero. I'll say a little bit about what happens when it's zero.
How was it that you passed from renormalization group flow to topological field theory in
Okay, I will go back. So I didn't say that, but so I'm describing. So what I'm describing is sort of the tangential direction here. So what is so near here, what do I have to do to solve the condition that I do have a translation invariant defect which is compatible with this perturbation? So it's a statement I can do order by order in perturbation theory in this CFT. That's what's happening. So that's why the condition can be entirely stated in conformal field theory. Okay. So this can also be stated algebraically. So now all the TFT will have disappeared, and now we're just doing algebra. So the TFT condition I had before is equivalent to this algebraic condition. So let's parse this a little bit. So we have fx, which lives up here, and it comes with a half braiding past anything in t. So I'm allowed to write a picture like this. Well, an omega was given as part of the data, and so the algebraic condition is this. So that's the condition I want to solve. Fix this, find all solutions to this condition. And the category of the solutions I call T for translation invariant with respect to X, Y, and omega for lack of a better name. And because you said omega maybe is 0 or not 0, I want to say a little bit what happens if omega is 0. So if that parameter omega, so if that's 0, then that morphism is 0. Then this side here becomes trivial, right? So that's just 0, the left-hand side. And then on this side, the condition becomes that f and g commute. And one way to make sure that that's always true is if we also set g to 0. So then that's also gone. And then we only left with one morphism f, which goes from fxd to d. And that structure appears on Gregor Schaumann's paper, if you want to look at that paper again. And so there's you see, the conference already did well at pointing at unexpected connections. And so we should talk about that now. Okay. So now we have arrived in algebra. So that's the end of the physics motivation. And I want to use this as an excuse to find that category interesting and try to learn things about it. Okay. So let's look at some properties. So this category is monoidal. I'll say later what the monoidal structure looks like. It is abelian and rigid if the category you started from is. The T also has to have a right exact tensor product, I should have said. But that's automatic because it's rigid. So if it's abelian and rigid, that works. It is different maybe from the category one usually meets. For example, it typically will have an infinite number of simple objects in it. And typically you will have situations that if you tensor two simple objects together, the answer is again simple. Right, so it's sort of a little bit far from the fusion categories one looks at usually. So by enlarging the class of topological defects you want to look at, you end up with a sort of more wild-looking kind of category.
But not always, right?
But not always. So I will in the presentation have a number of questions to which I don't know the answer, and I'd be interested to learn how there are methods to obtain the answer. One question is, when is this category actually non-trivial in the sense that we find non-trivial solutions of D, F, and G. So if omega is non-zero, I don't have a good mechanism to decide when is this category non-trivial. And an example of this is you can take your two braided categories to be the easing category, so 3 objects, braided category. You can take T to also be easing, just forget the braiding. Then the 2 objects X and Y, you just take them the sum of the 2 non-trivial simples. And then the omega, you take anything. And then you ask independence of the omega, how does this category look? And I would guess, but I don't know if it's true, that this category is just vector spaces, unless either omega restricted to one or the other summand where it can be non-trivial is 0. And so it'd be nice to have like a theorem which says, I at the moment don't. So that's the physics expectation. And we will say that maybe later again, this is because this deformation, so these 2 deformations are known to be integrable deformations and all the others are not. And I would expect that this being interesting is related to the deformation being integrable, but yeah, it would be nice to And that's now a concrete math question, so it has a concrete answer. But the question is, when is this category non-trivial? Okay. I want to next discuss a C star times C star action. It's not, it's maybe not really an action. So what I get is a family of functors. So we try to point again. So in this category here, I had these objects D, F, G, which have to solve this condition. Well, clearly, if you hand me two non-zero complex numbers, I can just multiply F by one number and G by the other number and omega by the product of these two numbers. And then I've got a new solution, right? And so what that does for me is it gives me a monoidal functor from the category T to itself, but with a rescaled version of omega. So all of these, so there's like a C star, well, there's a C star worth of these because you can multiply with a non-zero constant, but they're all equivalent. But that's it. Okay. So what does that look like maybe as a sort of a diagram of categories over a base space? So we have, if I take this product here fixed, then I'm pointing at some place in C star. And so over each point of C star, I now get one of these categories. And each of these categories still has one C star action left over, where I just take lambda here, and lambda tilde is now mu over lambda. Okay, so I have a C star family of these categories. They're all isomorphic, and each one carries a C star action. So what you can also do is you can take these parameters we had to 0. Well, that's perfectly fine. Then you end up at the category which sits over omega is 0. That's not equivalent, but there seems to be a process which allows you to take these categories in a controlled way into the 0 fiber, which is different. So that's maybe something I should know. But so what's sort of one question might be, what's like the appropriate math way of saying this? And you have this family, but then here there's a different fiber, but there's a controlled way of moving these in here. So that would be good. So why would that be good? Well, so what that process is describing, so this mu, this parameter, that's in a way parameterizing this family for you, right? So this mu corresponds to the mu here, and so varying this mu moves you on this line. Then moving this category back into the 0 fiber, that's the algebraic model of moving to the point where you're not perturbed. So moving that box back into here. And the thing I don't know how to do is to connect it to the other end. So that's a math question now. So is there a mathematical way in which we can state, can we move? So is there sort of, can we complete the C star to a P1 in some reasonable way? So is there like a fiber at infinity which we can predict from this structure? So that would be super interesting because it would give you information about what these infrared topological field series could look like. Okay, but I don't know the answer to that. That's sort of a question. So if somebody has ideas, please tell me. Okay, so what did I do so far? I had a physics motivation. I came up with maybe a slightly esoteric looking algebraic structure. Let me go back, which was solutions, which was this category, which had this data, and I wanted to find objects which solve these conditions. And it's always good if you then can find a similar structure somewhere else in mathematics, and you're like, oh, maybe there's some results about it, and it doesn't look totally off anymore. And the structure which you can find somewhere else in mathematics is Jeter-Drinfeld modules. So I want to now explain how this category T, X, Y, omega relates to categories of Jeter-Drinfeld modules. So the setting we're in is we take C to be a braided category, and H is an object in C, which is also a Hopf algebra. So it comes with a product and a co-product, and I'm not writing all the axioms. I'm just pointing at the one axiom where you need the braiding. So you have all the data of a Hopf algebra, But the Hopf axiom, the one that the co-product should be an algebra map, well, that asks you to define an algebra structure on the tensor product of two algebras, and that uses the braiding, right? So that's the place where in the Hopf algebras, you need a braiding to make sense of the axioms. Okay, so anyway, braided Hopf algebra. And as an example, and an example I'll need later is if I point at another object in C, I can look at the tensor algebra for C. So I need C to have direct sums and infinite direct sums for this to work. But if it has, then I can take the tensor algebra for X, so 1 plus X tensor 2 and so on. And then that's an example of a Hopf algebra in C. Okay, so next I want to do Jetter-Drinfeld modules. So remember our situation. So we have these two braided categories and they map through the center to some tensor category. And I now pick a Hopf algebra H1 in one of these categories and H2 in the other category. And I also pick a Hopf pairing which goes from H1 tensor H2, where I forget them both into T. So I'm not writing the functor and I'm not writing the forgetful functor here. So really this reads first do FC, then do forget, so that we are actually in T. So I need a Hopf pairing from H1, H2 into 1. And to say what that means, you need to remember that you walk through the center so that you have half braidings for H1 and H2. And then a Jetter-Drinfeld module for this pair of Hopf algebras in our category T would be an object in T together with two actions. So H1 acts from one side and H2 acts from the other side, such that a condition holds, and the condition is this. Right, so that's, so I copied this from a paper by Besbalov from 98, so not so new. And well, so if you've got one of these, then that's called an H1, H2 Jetter-Drinfeld module, and they form a category, and that category is automatically monoidal. So it's just the usual Hopf algebra tensor product, and then you can check that that still satisfies the Jetter-Drinfeld condition.
Yeah.
Because
So-
these conditions are practically the compatibility of the structures, right?
Say that again more slowly.
The diagrams are just simply saying that the structures are compatible from the left and the right.
Okay,
No? Am I mistaken?
well, so for example, so maybe, but I can't parse it that quickly. If you can state that as a compatibility condition, very good. For example, a Jetter-Drinfeld module is not a bi-module, right? Because the two actions do not commute, but they sort of the amount by which they not commute is measured by this condition.
Oh, okay, so it's not necessarily. Okay.
Right. Good. Jetter-Drinfeld modules, and so another thing. So so the place where one usually meets Jetter-Drinfeld modules, it's slightly different. So there you would usually have an action and a co-action, and then in that language where you have an action and a co-action, well, then this category is also braided. But if you write it like this, it's not automatically braided. So I will need to use this one, and that category is not automatically braided. It's always tensor, but it's not automatically braided. And the reason is that if these H's, if these are not dualizable, then you can't write a co-pairing for the Hopf pairing. Okay, so let's relate the Jetter-Drinfeld modules to the funny category I started with. So again, that's our setting. We picked two objects and we picked a morphism from X tensor Y into 1. Again, I'm not writing the functors anymore. And then the first thing you convince yourself of is that morphism, just you can sort of order by order, turn this into a Hopf pairing on the tensor algebra for X, tensor algebra for Y. So that arbitrary morphism gives you a Hopf pairing here. And then with that Hopf pairing, the category of Jetter-Drinfeld modules over the tensor algebra is monoidally equivalent to the to this funny category T I extracted from my physics motivation. Right? And as I said, this category not necessarily braided, and neither is this one. Right, so the mass object which we have extracted is now yet a Drinfeld modules over the tensor algebra. It may actually be more convenient to still work with this category because you don't have to worry if the tensor algebra exists in the categories you're looking at. But okay. So with that, I want to come to an example. And so maybe before I do the example, so that's sort of the general setup. We met this category out of deforming field series. It's related to yet Drinfeld modules. On that part, are there any questions or comments? If not, I will do an example. So let's look at the example. So the example is on the physics side is a perturbed free boson, which becomes something called the Sine-Gordon theory. And I just want to give the algebraic counterpart. So I pick a real number, R, which has the interpretation of compactification radius. So I will look at the free boson on a circle. Then the two braided categories, which I have to fix. Right? So here's again my cartoon of the data I need to point at to formulate the problem. So my two categories are vector spaces graded over the real numbers, vector R. This is braided via just this exponential. So that's my braiding. So that's my braided category. Okay. What's T? T is vector spaces graded by 2 copies of U1. Comes with a 3 co-cycle, but I don't actually need the 3 co-cycle, so I'll not talk about it. So that's T. Then I have to give these two functors, and I'll not describe the half braiding. I just describe the answer of going up here and then forgetting down to T. So notice C and D are the same. So now I want to give a functor from C to T. Use forgetful. And it takes a simple object in here. So that's the one-dimensional vector space graded by alpha to a simple object in T, which is a one-dimensional vector space graded by 2 elements in U1. And then there's a specific formula for these 2 elements, where X is some exponential depending on alpha, and the R I chosen. And so these I just pull out of my head. I'm not explaining where I got these from. I'm just saying in that example, that's what I want to use. And for the other one, for going from D to T, the only thing that changes is that the second U1 element becomes its inverse. So there's this minus sign here. Good. That's my example. So let's do a small sanity check. So let's remember this TFT picture. So I don't actually have a TFT in that setting, but that's in the gray physics motivation box. So it doesn't have to be mathematical. But I can now ask the question, if I label this by one of my objects in C, simple object, and this by one also in C, C was equal to D, what is the dimension of the space of point junctions? Right, and algebraically what this means is I should, sorry, let me go back a slide. I should use these two functors to take an object here and forget it to T, tensor them together, and ask, does it have a morphism to the tensor unit in T? Okay, so that's what I'm doing. I'm taking the object C alpha, that's my labeling the top line here. I'm forgetting it to T, taking C beta, applying the functor to move it into T. And I'm telling you that the answer is this. You can actually do that computation with the information on the previous slide. And I'm asking, when does this have a morphism to the unit? Well, the unit is the one-dimensional vector space where this is both graded by the identity, by 1. And so we get a non-zero point here precisely if the sum of these two numbers, alpha and beta, lie in Rz, and the different lies in 2 over Rz. Right, so that you can read that off instantly here. And if you've ever done the compactified free boson ever in your life, you have seen that. So that's the charge lattice of a compactified free boson, one-dimensional on a circle. Good. So that makes sense. And so now I want to choose the rest of the data. So I want to do an example. So I have to point at my two categories, and I have to point at two objects in these categories. So the X I want to do is a direct sum of two simples, namely these. So that's now I'm allowed to do this because so X and Y I choose the same. So in particular, if I take in X this summand and in Y that summand, then it satisfies these conditions, so I can expect to find non-trivial point junctions there. And so then the omega, which goes from X tensor Y to 1, so generically that space of possible omegas is two-dimensional, and I just pick any one element which is generic, so where none of these is accidentally 0. Okay, so that's the setup. And I claim that that setup is related to a certain quantum group, namely the quantum group for the affine SL2. And so to explain this relation, I first have to talk a little bit about affine SL2. We pick a complex number which is not plus or minus 1, can be a root of unity at that point. At some places later, I'll exclude that. Then UQSL2 is defined in terms of generators and relations. So we have E and K, and then we have these relations. So I'm not putting a restriction on when the power of K becomes 1. So we have infinitely, so it's not the small quantum group, so that's infinite dimensional. Then the affine quantum group, well, you basically get two copies of this which talk to each other. So now we have EI plus minus, KI and KI inverse, where I takes values 0 or 1. And you get two copies of these relations. And then there are some higher polynomial relations called quantum Serre relations, which I'm not writing down. But you can look this all up in a paper by Chari and Presley. So we have got these two Hopf algebras, this one and that one. And there's an algebra map between them, which is called the evaluation homomorphism, which depends on a non-zero complex number. And I've written it out. It's not so important what that actually looks like, but I just want to point. So there's on E1 and K1, it just nets it directly to these generators, and the others get scaled in some way. Okay. So we have an evaluation homomorphism. And so this will allow me to easily write representations of this more complicated Hopf algebra in terms of the UQSL2, which is maybe more familiar by just pulling back along the evaluation homomorphism. So I'll do that. So why am I talking about UQSL2? Because you can write down a functor from finite dimensional weight representations of the affine quantum group into this category T I defined in the specific example I just presented. So that's the R-graded vector spaces and so on and so on. And for the choices I made, I claim I get this functor with nice properties. So I can now reason about this category about which I don't know very much by understanding better the representations here of this affine quantum group, at least on the bit which is hit by this functor. So it's not an equivalence, but the part of this which is hit by that functor, I can now learn something about. Right, and the deformation parameter Q, and notice is related to this R, which on the field theory side has the interpretation of a compactification radius. Right. So now, after having stated that, I'm now allowed to just stare at this category. And so here are some properties it has. So I introduce the notation Vn of z to mean I take the n-dimensional irreducible representation of UQSL2, and I pull it back along the evaluation homomorphism. And so now I've got two parameters, a non-zero complex number and this n. And what n can be depends on whether Q is a root of unity or not. But okay, so I want these to be irreducible already for UQSL2, and then I pull them back. Right, so if you do that, well, clearly Vn of z is still simple because it was already simple for the smaller algebra. So that's not surprising. now if Q is not a root of unity, then you find, or rather Chari and Presley found, that if you tensor two of these together, the answer is this is still simple, right? So that's very different from the UQSR. So if in this situation where we not have a root of unity, then without having pulled it back to the affine quantum group, that would just decompose into a sum as one is used from SL2. But now, because we're in the affine case, this is actually simple. Unless the evaluation parameters satisfy a relation on their ratio, right? So there's some weird condition that if the evaluation parameters are related in a certain way, well, then that's not simple. And instead, you get short exact sequences, and I've got written an example here. So the algebraic structure is quite pretty, but also quite complicated. And so that's an instance of what I said in the beginning, that the monoidal category you get out of these line defects, which are translation variant, is more complicated in the sense that you've got often got these infinitely many simples, and you can tensor simples, and oftentimes the answer is not decomposable, but again simple. Right. We're doing time, not so. Oh, I should stop, right? Somebody wanting to stop me? Soonish. Goodie. So I want to also talk about the Grothendieck-ring a bit. So this, I'm only looking at finite dimensional representations. And so it makes sense to talk about, or it's interesting to talk about the Grothendieck-ring of this category. And I want to these simple objects Vn of lambda, I should have called that I defined on the previous slide. I now want to call the class in the Grothendieck-ring, I want to call that Tn of lambda. I've switched to lambda because that's will be a spectral parameter, and that's often called lambda. Okay, so that's an element in the Grothendieck-ring. And about the Grothendieck-ring, you can make some interesting statements. For example, again, Q not a root of unity, you can show that this is actually commutative. The Grothendieck-ring is commutative, which is surprising because the category is not braided, right? So it's sort of almost everywhere braided, but not quite. And but still, the Grothendieck-ring is commutative. And I will go back one slide. This exact sequence I had here, so the exact sequences I find at these special points, now turn into functional relations for elements in the Grothendieck-ring, like this one. And now, if you've ever done integrable systems, you've seen such equation that's called a T-system functional equation, or if you've done cluster algebras, you'll also have seen such equations. And so that's a relation, if I sort of may go back to the physics motivation. So these VNs now describe specific translation invariant defects, and the operators, the assignment of an operator to such an object in the category, that assignment factors through the Grothendieck-ring. And so therefore, the defect operators will, if they exist, right, so there are convergence issues and so on, but they would then satisfy these functional relations. And then so that maybe as an outlook is important because so this assignment, okay, so we go from here to T and to defect operators that factors through the Grothendieck-ring. The Grothendieck-ring in my example was commutative, so I get a large family of commuting operators. They commute, so I might be able to diagonalize them. The eigenvalues satisfy T-systems, and then you're in the sort of realm of integrable systems. So then you've got a T-system, you got TBA equations, and these are integral equations, you can try to solve them. So that's quite pretty. So this approach allows you to connect to another piece of mathematics, which is this integrable systems, where there are methods to then make also non-perturbative statements. And I think with this, I just want to list my questions again, and then I will stop. So one thing which would be important to know in that setting is when are there large families of commuting objects in this Grothendieck-ring. Another thing which would be interesting, which I didn't explain, is when does this have finite subrings, so things which close under products, which are on a finite number of elements. Then another vague question is, so that was all two-dimensional. Does it have a higher dimensional counterpart? I don't know, neither on the field theory side nor on the algebraic side. I don't know that. And so these are the questions I had earlier, and I'll shut up now. Thank you for letting me talk.
Like you could